Hello everyone. In this video, we are going to talk about van der Pol oscillation. Van der Pol is the name of a person. And the system is this circuit. So we have a linear inductor and a nonlinear resistor. So if the current flowing through the inductor is denoted as I, and the voltage decrease across the inductor is denoted as V, then V and I satisfy this equation. Here L is inductance, and it is a number, and I dot is the derivative of current I with respect to time, so I dot is the IDT. And the characteristic of this nonlinear resistor is given by this equation. So here negative sign, we have a negative sign here because the I that I use here, I is going up. It's this I, so it is going up, which is the opposite direction of the voltage decrease. So that's why we have a negative I here. So basically, we already have the differential equations for this circuit, and notice that the second equation has no derivative in it. And this formula, here, is directly related to van der Pol. And what I will do next is show you the graph of V and I with respect to time t. And I will also show you the graph in the phase space. So here the x and y coordinate represents voltage and the current respectively. And the way that this is graphed is that we start with an initial value of V0 and I0, and then we use the Euler method that we see. Okay, so from here we can see what is the next point after a small time interval, where is the next point, and after a small time interval, where is the next point, and then we kind of draw a curve like this. I want to make a disclaimer that the graph that you will see, they are correct graph, but the way that I graph them is actually is approximation of this system. So the graph that I will show you comes from a slight modification of the system. So here on the side of of the inductor, I'm adding a capacitor with really small capacitance, so it's almost like it doesn't exist. The graph that I draw is approximation of this system, but since I'm using Euler method to draw the graph, which is already approximation of the real system, so I assure you that the graph you see is the correct one. Now I will show you the graph of voltage and current with respect to time t. So the horizontal axis is time, the vertical axis could mean voltage or current. So the initial voltage is set to 5, current is set to 4, and I will click this button to increase time. So the red line is current, and the blue line is voltage. So it looks like the system is indeed oscillating. So the current red line is continuous, but the blue line, which is the voltage, has these vertical lines. So they look like it doesn't take much time for the voltage to jump from one value to the other. So it could be jump from a lower value to a higher value, or higher value to a lower value. So for the voltage, there is a sudden jump, and this is a characteristic of a van der Pol oscillation. Now let's see the same graph, same process. We will repeat this process, but in the phase space. So the horizontal line is voltage, and the vertical line is current. We're starting at this point. I'll click trace, to see the trace in the phase space. So now we are in a loop. So this is a typical graph for the van der Pol oscillation. So in the horizontal line, you have a sudden jump. Horizontal axis is the voltage. The voltage suddenly jumps from here to here. And then in the vertical line, you are moving slower. So now let's see those two graphs together one last time. So what you see here is that we started with a very big value, and then it converges to this cycle. This is called the limit cycle. Very quickly, and start oscillating there. What if we start from a smaller value? Step to 0. So if we start with smaller value, and we reach to the limit cycle very quickly, and then start oscillating there as well. Now let's look at the graph of V and I in the phase space more closely. This is the graph of the function negative I equals V times V squared minus 1. So an I and V, in the system should stay on this line, and it should satisfy this differential equation. So at the beginning, our initial value might be chosen that is not on this line, but it should quickly go to this line somehow. So let's just start a point on this line. And then there's the question, is are we going up or going down? So if you look at this equation, so the sign of I dot is the same as V. So here the voltage V is negative. So we know the di dt is also negative. So I is decreasing, so we are going down. So when we reach this point, we have a dilemma. So because here the voltage V is still negative, so I dot should still be negative. So according to this equation, we should still go down. But according to this equation, we should stay on this line and go up. So we have this tension, either go up or go down. And what happens is suddenly we jump to this point. Again, voltage is positive, and so the IDT is positive, so we will go up. And when we reach the high point, again, we have this dilemma between those two equations. One equation says we still go up, one equation says we go down, and what happens is we suddenly jump to this point. So basically, we are in a circle. So when we in the simulation that we saw before, the state travels slowly in the vertical line, and in the horizontal line it travels quickly, but it still kind of travels through this line because our system kind of have a capacitor. It's an approximation, so that's why you can see like a smooth, like a closed curve. But the actual solution to this equation should have a sudden jump, so this V is not continuous from here to here. So the point of this video is to give you a flavor of van der Pol oscillation. And this graph, you probably will see it in many other places, in many other systems. And yet again, this is an example that we can predict a key feature of the system, that is this sudden jump of voltage, by just analyzing the equations in its phase space without actually solving the equations.